Welcome back. So today I'm going to focus on the mathematics behind the eigenproblem. Now, of course, the first time we saw this, we were in oscillations and waves, and we were talking about just matrices and finding eigenvalues and eigenvectors. Well, in this class, we're going to have to extend the idea of the eigenproblem a little bit further. And so we're going to introduce concepts like eigenstates, which is sort of a generalized eigenvector. And of course, we've already talked about how measurements are really correspond to eigenvalues in many of these systems. So the eigenproblem is the thing where I'm trying to solve for the eigenstates of some operator. And what that really means is that I have some complicated mathematical thing, right, which I'm going to call capital M right here. And that complicated mathematical thing might be a big matrix operator or some other function that takes in a vector, right? Here my vector is psi, or it takes in a state, and then it outputs a state, right, which is going to be the right-hand side of this equation. But the state that it outputs is going to be proportional to the state that it inputs, right? And that constant of proportionality is the thing that we call the eigenvalue. And I want to talk about this in that sort of qualitative way because our operators are really going to be taking in states, right, and then outputting states. And there are going to be only very special states or very specific states for which the input state and the output state are in the same direction, right? And so that's the idea behind an eigenvector, right, or an eigenstate, is that somehow that state is special to the operator such that the operator doesn't really change it, but it spits out the same state, but with some constant in front of it. And that constant in front of it then is special to that specific state, right? Most of the time, different eigenvectors have different eigenvalues, but it somehow that constant of proportionality is linked to the state, and both of those things are special as defined by the specific operator. On this slide, I'm also showing a convention that we often do in quantum mechanics, and that is if I have an operator that I represent with some capital letter, here I have M, then the eigenvalues of that operator I often denote with lowercase, the lowercase version of that same letter here. I have little m. Okay, and when I get to, as I've written it here, these don't quite look like I've solved for eigenvectors yet because I haven't solved for eigenvectors yet. But I want you to keep your eye out, not just in quantum mechanics, but maybe in all of physics or all of life, for when you finally encounter problems like this, you'll see this kind of equation, right? That I have an operator that's some big complicated mathematical something acting on a state and outputting a state that's proportional proportional to the input state. And you'll actually notice that you've come across these many times, and it's something that sort of becomes fun to recognize. And so, in other words, if I want to replace those symbols with the words that we're talking about, right? I have some big complicated something, and if I spend the time solving for the eigenstates, I can oftentimes make my problem so much easier, right? Just because I can now replace that big complicated thing, right? That big complicated matrix or that big complicated operator, and I can replace it just with scalars as long as I input an eigenstate, right? And now maybe just to get your, to make that somewhat more interesting, if I have, I know that for an eigenstate, right, this is true, but since it's a linear equation, if I can take any state and decompose it into eigenstates, right, then I can do this for any state, right, as long as I've chosen the right basis to analyze the problem. Okay. And so if I spend the time to find the eigenstates and find the eigenvalues of a problem, that often pays out in the long run, because then I don't have to worry about the big complicated operators, because I've found the states of that problem for which those big complicated operators just reduced to scalars, right? And it's always nice to work with just scalars. So if we're going to do this with matrices, which is of course the thing we did in oscillations and waves, I have a problem that looks sort of like this, right? I have a matrix multiplying a vector, and I get out an eigenvalue times that vector. And now I want to spend just a couple of minutes and remind you of how to actually solve for these eigenvalues and eigenvectors in matrix for matrix operators, okay? And the strategy always is to find the eigenvalues first, right? And then for each of those eigenvalues, you're going to solve for the eigenvector, and we'll talk about that in just a second. Okay, so let's do a 2x2 example, right? One, because I want this video not to be 6 hours long, but also I'm only ever going to really require you to find eigenvalues and surely find eigenvectors for a 2x2 system, right? And we'll get to what do we do when we have a larger system. We'll get to that in a minute. But for a 2x2 system, we can do this quickly by hand, and so let's look at an operator that maybe we'll encounter later in class, but let me go with this operator here, okay? So my matrix is 0, 1, 1, 0. And I know from my eigenvalue equation that the matrix, right, times my vector is going to equal lambda times my vector, right? And I want to solve for the set of states for which this equation is satisfied. That is, what are the set of states for which lambda turns out only to be a scalar, and the state and the vector on the left-hand side is the same as the vector on the right-hand side. Just to recreate a tiny bit of math that you've seen before, we do this by, on the right-hand side, multiplying lambda by the identity matrix. So I'm going to represent that as a big capital 1. And so I have lambda times the identity matrix on the right-hand side, and I have the matrix on the left-hand side. Sorry for the extra line. I then subtract the right-hand side from the left-hand side, so m minus the identity matrix times lambda acting on the state is equal to 0. And now we get to this moral thing where, well, if this thing has to be equal to 0, then something on the left-hand side has to be equal to 0. It's not going to be the state, so somehow it must be this combination of m minus the identity times lambda. Okay, which means that this thing kind of has to be 0. Well, we'll require that the determinant of m minus 1 times lambda is equal to 0. Okay, so now let's do this for this matrix. So m is 0, 1, 1, 0, and then I'm going to subtract lambda times the identity, lambda 0, 0, lambda, and that's going to give me minus lambda, 1, 1, minus lambda. Okay, that's the matrix. Now, the determinant of this has to equal 0. So if I find the determinant of this combination, the determinant of minus lambda, 1, 1 minus lambda, is equal to, well, the determinant is the diagonals, which is lambda squared, minus the off diagonals, 1 is equal to 0, and therefore lambda squared is equal to 1, and therefore lambda is equal to plus or minus 1, right? Yes, this was a fun, quick example, but again, I'm really only ever going to require you to do this for 2x2 matrices, right? If we're going to do eigenvalues and eigenvectors by hand, 2x2 seems to be a place where I can ask you to do that. Okay, so now I've actually done the most important physics part of the problem, right? I've found if this thing was a real operator, if this was a piece of equipment that I could build, I would only have 2 possible measurements from this piece of equipment, and those 2 possible measurements would be plus or minus 1. Of course, now I want to actually solve for what the eigenvectors look like, right? And that's going to take a little bit more work because I have to solve for the eigenvectors one at a time. So let me do it just for one of them. And the one I'm going to do it for is the -1 eigenvector, just because I think that one's a little bit harder. And so maybe it makes sense to start with that. Well, I'm going to go back to my definition of the problem, right? So m acting on some vector is equal to lambda acting on a vector. I now know what lambda is for one of the eigenstates, right? So let's call this particular eigenvalue lambda 2, right? Because I don't know. Lambda 1 will be the positive one, lambda 2 will be the negative one. And so my matrix, which is 0, 1, 1, 0, acting on my eigenvector, which I don't know yet, so I'll just put in two unknown numbers, right? Because it's a two-dimensional vector, is equal to the eigenvalue minus 1 times AB. Now, this is a matrix equation, right? And so I have to do out the matrix multiplication on the left-hand side. It ends up that so this is 0 times A plus 1 times B. That puts B in the top. It puts A in the bottom, is equal to minus A minus B. And I was hoping, or we were hoping, right, that I would end up with two different equations, right? And I do have two equations. I was hoping to have two different equations so I could solve for what A and B are. And you'll notice that I get B equals minus A and A equals minus B. Those are not two different equations, right? They're the same equation. I know that A and B have to be opposite of each other, but basically I found that the second eigenvector, right, the eigenvector corresponding to this eigenvalue, is going to be given by A minus A. Well, that's not particularly useful, right? Because I don't have any equations left to be able to solve for what A is, okay? But you say, if this is a good basis, right? If this is if I'm going to use these eigenvectors to properly define a space, right? If I'm going to treat them as basis vectors, then probably my basis vectors should be orthonormal. And that would require that the vector dotted with itself is going to have unit norm. So what does that mean here? Well, it means that a squared plus a squared is equal to 1. And that means that a is equal to 1 over the square root of 2. And so my real eigenvector from a normalized point of view, or from a point of view where it's going to be useful to treat it as a proper basis vector, is going to have this 1 over the square root of 2 in the front. Is that physics? Well, maybe it's physics if I think that a orthonormal basis makes my equations better and fits into my mathematical model. Is it real? I don't know, right? I mean, like, I could have defined my spaces in a different way and required a different normalization. Is it unique? No, it's not unique, right? Because I chose I chose a particular solution to A, right? When I solved the equation a squared plus a squared equals 1. And so there's always a little bit of ambiguity with the eigenvector itself, right? And that is something that we just have to live with. If I asked everybody in the class to write down this eigenvector, probably most of you would get it to be 1 minus 1. But some of you would say that E2 was, say, 1 over the square root of 2 minus 1, 1, which is a totally acceptable solution to the eigenvalue problem, right? These two vectors are not the same, but they're both sufficiently good eigenvectors, okay? And that's just something that we have to keep in mind, that eigenvectors are not unique, even if I require them to have unit norm. Okay, so what do we do if I give you an a matrix that's bigger than 2 by 2? Well, we're going to go to Mathematica. And you remember how to enter matrices into Mathematica. You have to use this nested list syntax, right? So each row in the matrix is a list, which is in curly braces. And then when I have all my rows, I arrange them also in a list, which I have curly braces on the outside. If you ever want to check to make sure that your entered matrix is actually correct, or is actually what you mean it to be, right? You can always do the name of the matrix and followed by matrix form, and that will show you whether or not you entered it correctly. Now, this is just a 3 by 3 matrix, right? But again, anything 3 by 3 or bigger And I think probably Mathematica is the way to go to get your eigenvalues and eigenvectors. Can you do it by hand? Sure, go ahead. I'm going to do Mathematica. Okay, so to get our eigenvalues, well, we type eigenvalues, my matrix, and you'll notice that, boom, it just gives us our eigenvalues. Now, of course, it's a 3 by 3 matrix, so I sort of expected to have 3 eigenvalues. In this case, they're 2, 1, and 0. And now I can also find the eigenvectors by running the eigenvector command, eigenvectors on my matrix, and I get those 3 eigenvectors. Now I want to go back to something that I said a few moments ago about eigenvectors and being unique. Okay, so Mathematica is very good at finding the eigenvectors, but you'll notice a couple things about these. One, they are not normalized, right? These eigenvectors are clearly not normal. I guess the middle one is normalized, but they could in principle all have different lengths. Two, what I've noticed is that when we get eigenvectors from Mathematica, they oftentimes look funny compared to the way that I would calculate them by hand. And that's to remind us that eigenvectors are not unique, right? That if I can make choices on how they look even if they have unit norm. Now, Mathematica can normalize a vector, and it's probably best to do it one at a time, right? So you can use the normalize command, and let me call my eigenvectors here, and I'll choose just the first one, and it can normalize it like that. And so that's basically the process of asking Mathematica to normalize the eigenvectors as well. Now, what we should note is that the order that the eigenvalues come in, and the order that the eigenvectors come in are all the same, right? So if I have the first eigenvector, 1, 0, 1, is going to correspond to the eigenvalue 2 from the first list. Now, you can get everything at once by doing eigensystem, right, of my matrix. And that will give you, now this is a little confusing, right, because there's a lot of information here, because it's a list which has 2 elements. The first element is the eigenvalues. The second element is the list of the eigenvectors, right? And in this case, the order is a little bit easier to see. The first eigenvalue corresponds to the first eigenvector, and so forth. Okay, and that's how you can get the eigenvectors from Mathematica. Now, I'll also just point out that you can use Mathematica to do matrix multiplication, but you have to do it in sort of a careful little way. So, if I wanted to multiply my matrix, which I'm calling my matrix, and I wanted to do matrix multiplication of this with one of my eigenvectors, and I have to vectors. Let's say I do it with the first one. This little dot is the command that allows us to do matrix multiplication. And of course, it's the same dot that allows us to do dot products as well, right? But it works for matrix multiplication. And you can see that when I multiplied my matrix times the first eigenvector, which is this one here, 1, 0, 1, I got out something that was twice as big as 1, 0, 1, which verifies that indeed 2 is the eigenvalue associated with that eigenvector. So at least we were able to confirm that that this is the correct that's the correct eigenvalue for that eigenvector. So finally, I just want to say something about problems that aren't eigenvalue problems. Okay, aren't matrix problems. They're all going to be eigenvalue problems, right? I mean, the idea I come up with this equation and I say, oh, I recognize that as an eigenvalue equation. But what happens if the state, isn't a vector in the traditional sense, or can't be represented by a column vector? Maybe it's a function, right? Maybe it's e to the kt. And maybe my operation isn't a vector either, but maybe it's a derivative. Well, there are surely situations where derivatives of functions give me something that, oh my goodness, is proportional to the input, right? And that constant of proportionality looks a heck of a lot like an eigenvalue. And so I do want to keep this in mind as we go forward because we built so much great intuition for what it means to have eigenvectors, right, from a traditional matrix linear algebra point of view. But that concept of an eigenstate, the concept of an eigenvector, can actually be applied in many different places where I can replace complex operators, like the derivative operator, for particular functions to find eigenstates. And now you can see why I'd be uncomfortable calling e to the kt a vector, an eigenvector, but I don't mind so much calling it an eigenstate, right? And that's something that'll be interesting to us. All right, see you soon.